Hello everyone, I am Melanie Derksen and I'm going to present our work, Minimalism or Creative Chaos, on the arrangement and analysis of numerous scatterplots in immersive 3D knowledge spaces. In data analysis, scatterplots act as the first step in visualizing data. They help to get a first impression of data distribution by making trends and outliers visible. Previous studies show that classic spatial analysis tasks tend to be more accurate in immersive virtual environments compared to traditional 2D desktop setups. Now, to effectively conduct visual analytical tasks, it is essential to locate and recall the spatial arrangements of the data items. So here the spatial memory comes into play. It is a crucial part of human cognition that enables users to locate and recall item positions. A common strategy to support the spatial memorization of objects is the placement of reference objects, often referred to as landmarks. However, an overuse of landmarks can lead to visual clutter, which can distract the user and, as a consequence, reduce their performance. We wanted to combine research regarding spatial memory and immersive analytics. In order to get a structured overview of past work regarding spatial memory in and with the help of immersive virtual environments, we elaborated a design space. Overall, we identified 3 higher-level categories, being the main independent variable, which is the primary subject of investigation, so what was systematically varied. Then the items of interest, which indicate the type of objects or information that are to be memorized. And the item engagement, which denotes the degree of user involvement regarding the interaction with the items of interest. We decided to focus on environmental features as our main independent variable and explored the effect of varying amounts of landmarks on scatterplot analysis tasks. Our items of interest are plots, so 3D objects, and we had an active item engagement, so users were able to drag and drop their plots. This being said, we ended up with 3 conditions in our user study: empty as a baseline condition, desk with only one prominent landmark being a desk, and a virtual office with lots of room decoration serving as virtual landmarks. With this setup, we wanted to investigate, on the one hand, the strategies users employ to arrange scatterplots for analysis tasks, and on the other hand, the impact of varying amounts of landmarks on memory performance. Our user study consisted of 3 distinct stages, and after each stage we asked for task load and discomfort. At first, the participants had to arrange a total of 20 plots that spawned one after another. They had to think about an arrangement system that made sense to them. They were told to memorize their arrangement in order to perform some analysis tasks later on. Here we measured the overall time for the arrangement and explored the strategies users employed. When the participants were satisfied with their arrangement, the so-called blind recall phase started. Here the plots were replaced with equally looking black boxes, and the users had to recall 10 plot positions one by one. Here we measured the retrieval time and the items closer to correct one, so the time the participants needed to point and click and how many plots were closer to the searched one. In the last phase, the plots were visible again, and the users had to find answers to 5 analysis questions. Here we measured the time. All in all, we had 45 participants, which resulted in 15 per condition in our between subjects design. For the comparisons of the environments, we ran one-way ANOVAs and switched to Kruskal-Wallis tests if the assumptions were not fulfilled. We also supplement our reports with effect sizes for ANOVAs, and correlation and analysis were performed by computing Pearson's correlation. Since landmarks can aid recall, but an overuse can have a negative impact, we hypothesized that the environment will have an impact on performance in the blind recall. But a one-way ANOVA on the data did not reveal a significant difference between the conditions regarding the average number of items closer to correct one. But there was a small effect. On top of that, the retrieval time was not significantly affected by the environments. Furthermore, since landmarks seem to be important for the development of the spatial memory, we assumed that the absence of landmarks would lead to the highest task load in the blind recall and analysis phase. But again, one-way ANOVAs on the data showed that neither the mean task load in the blind recall nor in the analysis phase was significantly affected by the environments. The effect sizes were small and medium. Moreover, we assumed that longer arrangement times might be due to the development of a sophisticated arrangement strategy, and thus would lead to lower error rates and faster retrieval times during the blind recall. Correlational analysis revealed a significant negative linear relation between the arrangement time and the average number of items closer to correct one. So indeed, the more time a participant took for the arrangement, the less errors were made in the blind recall. Furthermore, we found a significant positive linear relationship between the arrangement time and the retrieval time, which means that it is exactly the other way around as we hypothesized. Based on these results, we assume that people who were fast in the arrangement could not remember their arrangement that well and tended to do fast guesses during the blind recall, while people with a sophisticated strategy spent more time on remembering where they exactly positioned the plots that were asked for. Well, our results so far are kind of disillusioning. There were no significant effects of the environments regarding memory performance, but the time participants took for the arrangement. That's why we will have a closer look if the arrangement strategy was a stronger factor than the environmental features. Overall, all participants used a large variety of arrangement strategies. Mostly, the arrangements were based on characteristics of the data rather than being connected to environmental features. For further analysis, our assumptions were that participants without a clear strategy mainly arranged plots based on their spawn order, while participants with a strategy ordered plots based on semantics rather than their spawn order. For this, we defined a deviation score, so how much the participant deviated from the initial spawn order in their final plot arrangement, so how far the plots which spawned after another were apart from each other in their final plot arrangement. Here we found a significant negative linear correlation with the average number of items closer to correct one. This indicates that arrangements deviating stronger from the spawn order were related to better results in the blind recall. To get a better impression, we will go through the final arrangements of two participants. Here we color-coded the spawn order from red being the first plot spawned and yellow being the last one, and also added the spawn numbers written in blue. In the first example, the user spent about 15 minutes in the arrangement and had the overall lowest error rate. Regarding the colored plots, one can see that they deviate strongly from the spawn order, and instead the plots were grouped by attributes in a grid-like manner, and plots sharing the same attribute were arranged along a line. This participant called the arrangement phase the most challenging one, which once again suggests that the effort invested during this stage paid off in the blind recall, leading to lower error rates. In contrast to that, in the second example, the user spent about 3 minutes in the arrangement and had the overall highest error rate. They said to follow a strategy that sounded pretty similar to the first example, but a deeper investigation showed that these intentions have been only partially realized. Instead, the arrangement was strongly inspired by the spawn order and not by the semantics. These findings suggest that the time and effort invested in the arrangement are a stronger predictor of performance than the environmental features. So conclusively, we introduced a design space that offers many opportunities for further research. We investigated the influence of different immersive virtual environments and plot arrangement strategies on spatial memory performance. Unexpectedly, our user study did not reveal a significant effect of the different environments on memory performance, but the time and effort invested in the arrangement. Future work might focus on how transferable our results are to professional data analysts and to different items of interest with a different level of information and complexity.